welcome back. Today we are going to talk about multi-layer neural network. We have already looked at individual neural units and we have discussed how they can represent linear functions, but actually we are more interested in exploring neural network to represent non-linear functions, and we can represent such non-linear functions by stacking the layers of perceptrons into various different kinds of architectures. So today we are going to look at feed-forward multi-layer neural networks, which is a particular type of connections in neural network, and also we are going to see various activation functions. As we have discussed in previous sessions, perceptrons are very basic single layer neural units. Though the learning algorithms are available, it is not possible to model complex nonlinear functions using a single perceptron, and hence there is a need to look at different kinds of or advanced neural networks, and here we are going to discuss multi-layer neural networks. Multi-layer networks can be learned by making use of more sophisticated backpropagation algorithm, and these networks are capable of representing a rich variety of non-linear decision functions. A multi-layer neural network contains more than one layers of artificial neurons or nodes. They differ widely in their designs. Typically, they have at least one input layer which sends weighted inputs to a series of hidden layers and an output layer at the end. So, input layer, hidden layers and an output layer. Let us see diagrammatically one simple example of a multi-layer neural network. So, as you can see in this figure, we are having the inputs x1, x2, x3 up to xn. So, these inputs actually are denoting our input layer. Now, this input layer is having connected with the hidden layer. So, in hidden layer we are having m number of hidden neurons. Every node in input layer gets connected with the hidden layer neurons. Associated with these connections we are having the weights. So, the weighted inputs are being sent to the hidden layer neurons. Further, these hidden layers are connected to one or more hidden layers, and ultimately the last hidden layer is connected to the output layer. Output layer may have more than one neurons as well. Whatever you are looking at in this slide is an example of a layered feed-forward neural network. This is a feed-forward neural network because the inputs or these connections that we have drawn are unidirectional. Inputs are given to the first hidden layer, then first hidden layer connections go to the second hidden layer and so on, and finally the inputs or rather the connections from the last hidden layer go to the output layer, and all those edges are in single direction or in one direction. There are no edges, those are going in the backward direction, and hence this kind of a neural network is known as feed forward neural network. This is called layered network or multi-layered network because we have organized the neurons into several layers. So layer I gets connected to layer I plus 1, I plus 1 gets connected to layer I plus 2, and so on. So this is the basic architecture how multi-layer neural networks are organized. Let us see one more architecture of multi-layer neural network wherein we are having input layer, two hidden layers and an output layer. So as I mentioned earlier, we may have more than one hidden layers, and all these layers are interconnected so as to get the output. As I mentioned earlier, output layer may have one or more neurons. Further, all these connections in between the layers are associated with the weights, and how to manipulate or learn the weights, we are going to see the algorithm for learning such kind of a multi-layer neural network, and the algorithm is popularly known as backpropagation algorithm. Now, if we would like to construct such kinds of multi-layer networks, what type of neural units we should use? Should we use perceptrons at multiple layers having the activation function as a threshold function, or whether we should go for something else? Now let us look at the perceptron once again. So here is the perceptron wherein we are having the inputs from x0, x1 up to xn. Associated with the inputs, we are having the weights w0, w1 up to wn. We are having the weighted sum computed by the neuron and the activation function. So typically in perceptrons we are using the thresholding function as the activation function, and we are getting the output as 1 or 0. So the expressions those we are using are given here: y equal to 1 if the weighted sum is greater than or equal to 0, and it is 0 if the weighted sum is less than 0. So this is a normal thresholding function, and by making use of this thresholding function as the activation function, we are going to make the decision whether output is 1 or 0. So if the weighted sum wixi is greater than or equal to 0, then the neuron gets fired, so output is 1. Otherwise the neuron will not be fired and the output is 0. Now diagrammatically the thresholding function can be plotted like this as shown in this figure. So in case of such kind of a thresholding function, what we can observe is there is a sudden change in the decision. Say for example, if we are talking about our old example whether we should go for watching a movie or not, say for example, and if we have set the threshold say 0.5, and if depending on the inputs and the weights, if the weighted sum comes out to be say 0.49, then the decision would be 0, that means do not watch the movie. And if the weighted sum is say 0.51, then suddenly the output goes to 1 and we say that we should watch the movie. So the basic perceptron is using the thresholding function as the activation function, and as we have discussed earlier, the thresholding function is not differentiable and it is not suitable for the algorithm like gradient descent. And we have already seen while learning or while discussing the learning algorithms for perceptron, if we would like to go for gradient descent, we cannot use the thresholding function as the activation function, and for making use of gradient descent algorithm for learning, we made use of a linear function, because the linear function is a differentiable function and hence we may use that for gradient descent. But even though we used gradient descent and we used the linear activation function, we have observed that it is not suitable, or the perceptron with the gradient descent learning algorithm may not be suitable for learning more complex nonlinear functions. Thus, while going for multi-layer neural networks, even though we go with layers of cascaded linear units, we cannot represent complex nonlinear functions, and thus we need to go for something extra. Thus, what we actually need is a neural unit whose output is not only a nonlinear function but also it is differentiable. And the solution for this problem is to make use of a sigmoid function or a logistic function as the activation function. So the sigmoid neuron that uses a sigmoid function can be depicted here. So it is similar to that of the perceptron, only the difference is the activation function in perceptron was the thresholding function and later on we used a linear function, but in sigmoid neuron we are making use of a sigmoid function or the logistic function as activation function. Thus, in case of sigmoid unit, the threshold output is a continuous function of its input and not a discrete step function. If you remember, we have learned this sigmoid function or logistic function whenever we learned logistic regression. In general, the logistic function is defined as the function phi of z is equal to 1 divided by 1 plus e to the power minus z. So whenever we apply this sigmoid function here with neural networks, the z becomes the weighted sum. So our output y can be defined as y equal to 1 divided by 1 plus e to the power minus summation over I equal to 0 to n wi xi. So if you look at this particular term, this is nothing but w transpose x. So it is 1 divided by 1 plus e to the power minus w transpose x. And now if we plot the sigmoid function, how it looks, please see here. On the horizontal axis we are having z, on the vertical axis we are having phi of z, that is the function of z, that is the sigmoid function is being plotted. And we can observe here, for a wide range of input domain we can restrict our output between 0 and 1 by making use of this sigmoid function. So if you try to interpret this sigmoid function with this plot, you can observe that as the input goes to the plus infinity, then the output reaches to 1, and if the input goes to minus infinity, output goes to 0. Also you can observe here, if the input is 0 the output becomes 0.5. So in terms of neural network, here the input is nothing but the weighted sum wi xi. So if the weighted sum goes on increasing beyond 0, then the output will become near to 1, and if the weighted sum goes below 0 or negative, then of course the output will go towards 0. And of course we can interpret this sigmoid function in some other way also, in terms of probability. So once again, referring to our movie example, instead of having a drastic decision that say for 0.49 the decision is no and 0.51 the decision is yes, instead we may interpret this in terms of some probability values, like 49% chance that we should go to watch the movie and 51% chance that we should go to watch the movie. So this seems more realistic. Of course we may apply the thresholding concept here at 0.5 once again, so that we may transform the result in terms of 0 and 1. So to summarize, the thresholding function is not smooth, it is not continuous at the threshold, and it is not differentiable, and hence the thresholding function cannot be used for gradient descent. Whereas if we go for the sigmoid function, its output ranges between 0 and 1. It is increasing monotonically with its input. The function is smooth, continuous, and also differentiable. Because it maps a very large input domain to a small range of outputs, it is also referred as the squashing function. Further, as this function is differentiable, the gradient descent learning rule can make use of this function for learning the neural unit, and hence if we go with this activation function, or if we go with whatever we referred as sigmoid neuron for constructing the multi-layer neural networks, then it is possible for us to come up with a backpropagation learning algorithm that also makes use of gradient descent. So in the next class we are going to discuss about the backpropagation algorithm, and we are going to make use of such kinds of sigmoid neurons to form the multi-layer neural network, and we'll see the learning algorithm to learn the weights for this multi-layer neural network. There is a variety of activation functions, and that can be used depending on some architectures. So we have here the summary of activation functions, those can be used. So we have identity function, we are having the thresholding function or binary step function. We have a family of sigmoid functions. One such function, sigmoid function, that we have seen is the logistic function. Also we are having another function in the family that is known as the tanh function. So that can also be used as the activation function while building the multi-layer neural networks. We are having arctan functions. The most popular nowadays is the function known as rectified linear unit or ReLU function, and this function is also being used in the popular deep neural networks. We are having parametric rectified linear units, the exponential linear units, and so on. So we are having here listed all those functions with their plots so that we can understand the behavior of the function. Also, we are having the mathematical expressions for the functions and the derivatives. So, as we can see here, except the thresholding function or the binary step function, all other functions are differentiable. So, please go through all those functions. This is for your information. Let us stop today, and next time we will be looking at the backpropagation algorithm to learn multi-layer neural networks. Thank you.